Okay, hello everyone to today's seminar after our short New Year's break. And it's my, first of all, great pleasure to wish all of you a happy, successful, and especially healthy New Year 2022. And yes, I'll hand over in a few seconds the microphone to Sergey Shary. And yes, since Sergey is situated in Russia, also to everyone in Russia, a happy New Year according to the old Julian calendar. And yes, let me introduce our today's speaker. Sergey is with the Federal Research Center for Information and Computational Technologies, and also with the Novosibirsk State University in Russia. And yes, since 2007, he's a professor at the university in Novosibirsk. And before that, he defended his Doctor of Science degree in 2000 with a work entitled The Interval Algebraic Problems and Their Numerical Solution. And in 1992, he received his PhD degree from, let me check, the University of Mathematics and Mechanics in Yekaterinburg. And now the floor, Sergey, is yours, and we're looking forward to your presentation on enclosing versus non-enclosing measurements in interval data processing.
Thank you for the introduction. As you told us, for many years I've been engaged in research in interval analysis and its applications to practical problems in engineering, mathematical modeling, natural sciences. And in the last decades, I decided to switch to data processing problems when you should take into account uncertainty expressed by intervals. And first of all, I would like to present you a brief introduction to the problems, data analysis problems, and the interval uncertainty. The fact is that observations and measurements are always not precise, and we have some errors that are inevitable in process of measurements, and how to process them depends on what uncertainty model we accept in our analysis. A traditional choice is probabilistic error model initiated by Gauss, Laplace, and many other prominent researchers 2 centuries ago. And in this model, errors of observations and measurements are considered as random variables in the sense that probability theory understand them, and we know more or less exactly probabilistic characteristics of these random variables, the shape of distribution, its numerical parameters, and so on. But very often, especially in the 20th century, with its huge industrial practice, this model proved unsatisfactory because we do not know probabilistic characteristics of the errors, and sometimes we even do not know that the probability theory is adequate to describe these errors. And an alternative model to describe the uncertainty is interval description. When you specify only 2-sided bounds for the values of interest, and in our case, 2-sided bounds for measured quantities, or which is equivalent, we specify an interval, lower A, upper A, for an unknown quantity. The pioneer of this approach was a Russian or the Soviet researcher Leonid Kantorovich in 1962. And below we can see a list, not complete of course, by researchers who followed him and developed this approach in our country. And in Western countries. Leonid Kantorovich is an outstanding mathematician, very well known to pure mathematicians because he has created a theory of, for example, linear topological ordered spaces, and where he obtained fundamental results. Also, he was one of the creators of linear programming. He studied researches in this field before the World War II in 1939, and he invented the dual simplex method, in fact. After the World War II, in 1945, George Danzig invented primal simplex method, and so they both were creators of the linear programming. And Kantorovich got a Nobel Prize winner for his invention because he positioned himself as an economist. Well, jointly with Koopmans in 1975, got the Nobel Prize for outstanding contribution to control of resources, distribution, and so forth for purely economical substances. But in the core, in the mathematical core of this technique was linear programming. So he was a researcher who knew very well linear inequalities, technique connected with linear inequalities and their solutions. In 1962, he published a paper. You can see its front first page, Siberian Mathematical Journal, volume 3, number 5. Kantorovich about some new approaches to computational methods and processing of observations. Introduction, and after a short introduction, actually theory of interval analysis in half-ordered linear spaces was outlined. Not constructed in details, but outlined briefly, but it was sufficient. And applications of this theory, he did not use the word interval, but actually his constructions were purely interval. And the page 707, you can see section, some problems of applied mathematics and problem of processing observations. This picture doesn't relate to the first item, but anyway, you can see two-sided graph similar to what we plot in our interval papers, for example. But the first item is illustrated by this short formula. You can see two-sided inequality imposed on a linear function. Li is a measured value plus minus delta, and for every index I. That is, Kantorovich wants to construct a linear function on the uncertainty and output variable when we measure it. So instead of the classical picture that you see in connection with the data fitting problem with regression analysis, Kantorovich considered something like this. Well, we have to construct a line that goes through all these uncertainty intervals, uncertainty segments. This is not the most general problem statement, and of course you can imagine that on input variables x are measured with uncertainties too. So the most general situation is described by this picture. You have cloud of boxes. I will call them uncertainty boxes or measurement uncertainty boxes. And you have to construct a line, a graph of the function from a prescribed family that goes through these uncertainty boxes or best fits them. And the first Western article on the subject was in 1968, was a paper by Schwette, published in IEEE Transactions Automatic Control, and he pronounced almost the same ideas, but he bounded uncertainty regions by ellipsoids. Yes, it is not boxes, but I think it is an interval analysis too. Far branches of interval analysis as well. I want to say that this line of research gained very, very intensive development, and you can see cover pages of two books published, Applied Interval Analysis. I see that we have an author in our audience, Professor Zhelen, and a very solid book cover on the right, Bounding Approaches to System Identification. System identification is another name, yet another name for the problem that I consider. It has many, many names. Data fitting problem, curve fitting, line fitting problem, identification problem, regression problem, within statistical context, etc., etc. But in essence, it is all the same. What you see on the left is a cover of a book consisted of surveys published in 1996. Well, and so when I started my research in interval data analysis, yes, I was sure that this branch of science is well developed. Yes, it is very solid. Well, but a plot twist. I got some nice results, I think, and I decided to publish them. Yes, and since my results relate to statistics and data processing, I wanted to publish my paper in a journal with the respective scope. And I have chosen Advances in Data Analysis and Classifications, Springer Journal, high-ranking journal that presents research and applications. Well, in many, many aspects of data analysis, I've sent my manuscript to the journal, and after several months, I got the following response. Dear Professor Shary, reviewers' comments on the book have now been received, and they have advised against publication of your work, and details are as follows. This paper faces the problem of uncertainty and imprecision and variability from a strictly numerical point of view, confuting the statistical theory of the regression model. Moreover, the author ignores papers on regression and interval data, for instance, and a spacious list of articles devoted to regression of interval data analysis in some unknown sense followed. This is just the first item. This way, I got acquainted with the so-called symbolic data analysis. So you see, and the key names in the symbolic data analysis: Bellard, Lynn Bellard, and Edwin Diday. Edwin Diday is a French researcher from Paris. Well, who started their research somewhere at the end of the last century and invented the so-called symbolic data analysis, conceptual statistics and data mining. Well, I discovered that a lot of books, publications on the subject exists. So I my research with interval data analysis seemed to be outdated. Well, not at the state of the art interval data analysis. The next two slides are contents of this book, and you can see. Do you see in the third chapter, section 3.3, interval valued variables, and section 3.5, modal interval valued variables. Do you see? My question to the audience. Because the font is not so large. The next page, regression analysis. Section 6.3, interval valued variables. And again, and you can see that interval valued variables are everywhere in symbolic data analysis. Well, so yes, I was somewhat wrong sending my paper to this journal. Another books on the subject, clustering methodology for symbolic data. And you can see the same boxes, rectangles, and on the cover page. Well, Lindelart, Edwin Day. One more book, Symbolic Data Analysis again. Yes, you can see two-dimensional intervals on the cover. So people are processing interval data for more than 20 years. Eventually, I have published my long-suffering article. That was a good journal, Advances in Data Science and Adaptive Analysis by Gold Scientific. But the questions remain. The questions remained, so that I decided to ask the authors of the symbolic data analysis through the ResearchGate, what is the relationship between the symbolic data analysis applied to intervals and interval data analysis that existed since 1960s? This is a screenshot of my post at ResearchGate under the book Symbolic Data Analysis. I showed you its cover. Two comments are my comments. The first one is you can write. One of the main particular types of symbolic data studied in this book is interval valued data, but processing of interval data has been considered long before Billard and Diday, since the 60s of the last century, and a large number of studies have been devoted to it that are based as a rule on the technique of interval analysis and supported by good computational methods. By the time Billard and Diday published their first work, these interval methods were summarized, for example, in the book, and I cite the above volume, bounding approaches to system identification, a collection of surveys on interval data analysis. What is the relationship between the approaches and results of the symbolic data analysis by Billard and Diday, and the results are outlined in the book cited above? What methods are preferable to apply in various practical situations? And the second post, somewhat later, was a question about the book by Luc Jolien, Queter, Divry, Walter, Applied Interval Analysis, because it is a very widely known book, and I dare say that the authors of symbolic data analysis should know, well, if they organize a Google search, for example, according to the key phrase interval data, interval identification, yes, so this book is one of the first results. In 2001, the book Applied Interval Analysis was published, devoted to implications of interval analysis methods. And chapter 6 of this book is called estimation, and it describes parameter estimation, state estimation in technical system, which is essentially the same data fitting problem that the regression analysis deals with, although called somewhat differently. Again, a question similar to that from my previous comment. How do the methods of symbolic data analysis, elaborated by Dillard and Didet, relate to the methods from the book by Julien, Kiefer, Didet, and Voltaire? You can see that my posts are dated by April 25, 2020. That is 1.5 years ago. No, more than 1.5 years ago, almost 2 years, and no answers were given since that time. Well, if they don't want to give us the answer, we have to give this answer by ourselves, because the situation is totally unnatural. It is a very bad situation when two disciplines exist in parallel, they apply to the same problems, and mutual relationship of these disciplines is unknown. The researchers from these streams, they do not contact, they cannot characterize specific features of the opposite approach, and so forth. So what should we say to our customers? Well, the main question, when should we apply symbolic data analysis, and when should we apply interval data analysis, classical interval data analysis? Well, so I have to give a short survey on symbolic data analysis in interval data fitting. If you look at Wikipedia, yes, it has an article called Symbolic Data Analysis. You can read that symbolical data analysis is an extension of standard data analysis, where symbolic data tables are used as input and symbolic objects are made output as a result. And specific type of symbolic data are interval data. The data units are called symbolic since they are more complex than standard ones, and blah, blah, blah. And symbolic data analysis is based on 4 spaces, and it is not clear from this text what is characteristic features the symbolic data analysis is applied to interval data. So we decided to give us a way of a more narrow problem, data fitting problem, regression analysis problem applied to interval data. It is a more easy task. I use the following publications. First of all, publication by Billard and Didet in 2002. And then publication by Brazilian researchers, publication by Korean researchers, Korean and Chinese researchers, and a very good survey given by these 3 guys from the United Kingdom. Unfortunately, this is only archive paper, but with very good quality. So, and to facilitate my goals, I also use a presentation given by Sonia Dias and Paula Brita, researchers from Portugal, at the conference in Buenos Aires in 2015. It has a good survey on regression for symbolic data, in particular interval data. It consists of 2 parts, and the first part of the presentation is devoted to linear regression for interval value variables. Paula Brita is a real person. She works in the University of Porto and active research in symbolic data analysis. So thanks to her, and I use her for presentation. Linear regression for interval valued variables. State of the art in 2015. You see a lot of methods, but it's better to go further and to read the next slides. The first idea with the symbolic data analysis was outlined by Billard and Diday in 2000. And you see that coefficients of the model are estimated by applying the classical model to the midpoint of the intervals. Classical model is a classical least squares model. So instead of this picture that I showed you previously, you have something like this. Only centers of intervals in interval uncertainty boxes obtained after measurements are taken into account. And what about the radii? Well, at the first stage, in the very first paper dated in 2000, they did not think about that. So it is a very naive approach. And they realized that after 2 years and proposed to apply linear regression models for lower and upper bounds separately of the uncertainty boxes. So instead of centers, you take into account points lower left and upper right, and construct two regression lines. And the drawback of this approach is evident. You can obtain two intersecting lines in such a way that the upper line intersects the lower line, and they provide you with negative interval of the angular coefficients, negative, not negative, improper interval of the angular coefficients, where the upper bound is less than the lower bound. Well, the estimated value for the upper bound of the interval may be smaller than the lower. Yes. This can happen if there are negative coefficients of the model. Yes, and the next research, they overcome this drawback. Brazilian researchers, they proposed to take into account the constraints imposed by the nature of the regression, and the two research dated in 2008 and 2010 overcome this drawback, so they get better results. But anyway, you can feel the flavor of the whole approach. They treat intervals in a way totally different from ours, from the way that we understand intervals in interval analysis and interval data analysis. Yes, they also process interval, but their interval differ from our intervals. So it is necessary to understand, to comprehend the whole approach. And the first question, does this even make sense? All this activity. So approach of the symbolic data analysis to processing interval data is in some sense perpendicular to ours. My answer is yes. It makes, to some extent, makes sense. And to present you more solid arguments, I want to remind you of the so-called correspondence principle. The correspondence principle in the methodology of science is a statement that any new scientific theory must include the old theory and its results as a particular limiting case. So the conclusions of new theories in the area where the old classical theory was valid passes into the conclusions of the classical theory. So you have something like inclusion. Something like this. New, old. Inclusion. Because we could have another diagram, by the way. And methodological significance of the corresponding principle lies in the fact that it can serve as a means to construct and correct new theoretical systems, new systems and concepts. The creator, father of the correspondence principle was Niels Bohr, who proposed it in his famous works in 1913, 1918, to explain the mutual relationship between the emerging quantum mechanics and traditional physics and micro objects. It was necessary, the correspondence principle was necessary to ensure continuous gluing of the new physics of micro objects with the classical physics of macro objects. And the latter perfectly describes, the classical physics perfectly describes and explains huge number of phenomena around us, and we cannot simply reject it on the ground that it is just old, unfashionable, and so forth. Another popular example of the applying corresponding principle is that in the special theory of relativity for small velocities, we obtain the same equations of motion as Newton's classical mechanics. And so forth. Many applications of the corresponding principle since the time that Niels Bohr advanced it a century ago. And the more so, the corresponding principle has a broad methodological meaning, because it can be applied not only to physics and natural sciences, but also to mathematics, computer science, for example, other scientific disciplines. And we can apply it to our area, to processing interval data. And if so, then the corresponding principle requires that good and reasonable interval methods in the limit when the width of interval data intervals tend to 0, switch to some methods for processing point data. Because real numbers are particular case, limited case of intervals. Okay. We can use the corresponding principle in our situation to check the adequacy of our concepts and our methods, to reject evidently unreasonable methods. And I want to say that symbolic data analysis for processing interval data is in agreement with corresponding principle, because if we squeeze interval to points, then the procedures switch to classical statistical procedures. At the same time, not all interval data processing methods proposed so far are consistent with correspondence principle. And we squeeze intervals, uncertainty intervals. Sometimes we get empty information set, so to say, and we say, we have outliers, and unfortunately, we cannot produce an estimate of the parameters. This is bad. So after this short outline, I want to switch to the comparison between symbolic data analysis and interval data analysis. What is the difference between symbolic data analysis applied to intervals and classical interval data analysis? This is the main purpose to give an answer to the question is the main purpose of my presentation. Let us look at them. First of all, we can notice that the basis of symbolic data analysis applied to intervals is the traditional techniques of probabilistic mathematical statistics, the least squares methods, sometimes other statistical methods, etc., etc. And the basis of the classical interval approach is the idea of approximating interval data, taking into account their specific nature, the interpretation of two-sided corridors within which we have to pass our graph of the regression line, etc., etc. So usually no probability at all in our approach. So because of this, we can apply interval data analysis to the situations with small samples. The problem of small sample sizes doesn't exist in interval data analysis, strictly speaking. But I think that this is not the characteristic distinction. In fact, in symbolic data analysis, the main assumption that true value of physical quantity lies within the two-sided bounds that we get as a result of the measurement process, which is equivalent that true value belongs to the interval, is not valid. They do not take it into account at all. And this is the main feature of the symbolic data analysis. You can ask me, do data intervals make sense then? I think that the answer is yes, of course, if nothing else is given to us. Because checking whether this membership is satisfied or not, it is not easy at all. No. If true values are not included in the measurement uncertainty boxes, what is left for us in our data processing? Something remains, yes. The only criterion remains to determine how good or bad our result is. It is the distance to these boxes, deviation from the uncertainty boxes of our estimate or regression line function, graph function in the data fitting problem. But we, in this process, we perceive uncertainty intervals as a kind of integral objects, opaque objects. Yes, they do not guarantee to contain true value of the physical quantity, but anyway, we do not have anything else. And we have to use this information in our analysis and the solution of our problem. So let us do that. In this connection, I want to introduce two definitions. Enclosing measurement. Definitions of enclosing measurements and non-enclosing measurements. Enclosing measurements, or maybe covering measurements, alternative term. In Russian, we call it накрывающие измерения, which means covering. But in English, taking into account that the term enclosing is very thoughtful, I think that enclosing measurement is good as well. Enclosing measurement is an interval measurement result that is guaranteed to contain the true value of the measured quantity, measured value. And a measurement for which it cannot be claimed that it contains the true value of the measured quantity will be called non-enclosing, non-covering. So it is not a direct negation, but a mild, a weak negation. We cannot be sure that the true value is in non-enclosing measurement. Illustration for point true values. we have measurement interval, and it contains true value, and non-enclosing measurement on the right. And sometimes true value as a physical quantity is an interval. Yes, that may be in many situations. And then we just reformulate this definition that enclosing measurement is an interval measurement that is guaranteed to contain the interval of the true value. So, but usually we process not separate measurement results, but collection of such measurements, samples called samples. And a sample of interval measurements will be called enclosing sample, covering sample, if the dominant part, majority of its measurements are enclosing or covering. And the sample is called non-enclosing, non-covering, if the dominant portion of its measurements are non-enclosed. You can see that I use non-strict terms, dominant part, non-dominant. This is dictated by the practice. I do not want to generate purely theoretical definitions, because the simplest way would be to call enclosing sample a sample that contains only enclosing measurements, but that would run contrary to the practice of measurements, to the real practice of data processing, where errors and outliers are inherent in data. And so if we require that all measurements are enclosing, this is unrealistic. And so detecting outliers, it doesn't have sense in such situation. So I use such mild formulations. So my conclusion is that interval data analysis is the analysis of enclosing or covering interval data, because we essentially use the fact that our estimate should lie within the interval, every interval measurement result, and so forth. And regression line goes through uncertainty boxes and so forth. And symbolic data analysis is the analysis of a non-enclosing or non-covering interval data. So they mutually complement each other. They produce a orthogonal or perpendicular vectors basis. It's better, I think, for real practice of data processing. And having realized that, we were able to provide a further development of symbolic data analysis for intervals. This part of my work is carried out jointly with my student Maxim Zvyagin. So if so, then we can construct a nice data solution to data fitting problem with interval data. We should assign a distance between the uncertainty boxes and the line, aggregate individual distances for separate boxes into a total one, and then minimize this total distance by optimization techniques that would provide us with the best fit line, as my previous methodology shows. I do not know, is this a symbolic data analysis? I think it is an interval data analysis, but interval data analysis for non-covering, non-enclosing data. So the first step is to determine distance between a point and line and uncertainty interval, separate uncertainty interval. And you can define it as the maximum distances between this point and points of the interval. Then we extend that to box. So for the entire box, distance between this line and uncertainty box, we take it as the maximum for over all these points on the line. correspond to vertical intersections. Then, if we process a sample of interval data of this kind, we take a vector of residuals, a vector of deviations, and we have to take its norm in any sense. Well, deviation of the regression line from interval data, it is just a norm of the vector made up of separate deviations for uncertainty boxes. And you can take this norm in any way. It may be Euclidean norm, two norm, it may be one norm, weighted Euclidean, and so forth. We take Chebyshev norm, maximum absolute values of the component. Then we minimize the total deviation by develop non-smooth optimization methods that we applied in our previous techniques. And what we get, it's very interesting. Let us consider an example. Let us construct a linear function with a free term beta 0 and angular coefficient beta 1 for such data. I assume that the input variable doesn't have any uncertainty. It is known precisely 1, 2, 3, and we have uncertainty intervals only on output. So the data looks like this. And yes, what regression line should go through these uncertainty intervals? Well, to my mind, the best line would be parabola, but it goes like this. But if we restrict ourselves to only linear functions, then the problem becomes very, very interesting. Let us solve it by two techniques, for enclosing data and for non-enclosing data. For non-enclosing data described in my previous 3 slides. So for enclosing data, I have to substitute the data into the expression of the function, getting the interval equation system, and we have intervals only in the right-hand side. So we have such interval system of linear equations and its solution set, both united solution set or tolerable solution set. So either weak or strong compatibility, they coincide with each other because no intervals are on input. This is the solution set. We call it information set of the problem. It is non-empty because you can see that. Do you see my cursor? Yes.
Yes.
You see that the line that has negative angular coefficient, and starting, for example, from the point 0.03, it goes through all these intervals segments, and many more lines starting from the point 0.2, 2.2, and so forth. They go through all these uncertainty intervals. So the solution set is non-empty. It looks like this. Well, and the angular coefficient beta 1 is mostly negative, while the free term stretches from 2 to 3. It is 0. Well, and yes, it is the set of parameters compatible with this data. Well, with this data. And to choose a point estimate, we can use, for example, maximum compatibility method that I described in my publications. For example, in that mentioned earlier, from Advances in Data Science, from publication from Journal of Global Optimization, and the best fit line that provides us with best compatibility of the interval linear system. It has the following form: minus 0 to 5 plus this line looks like this, a green line. And what about, it is a method for enclosing data. For non-enclosing data, if we take these uncertainty intervals as integral objects and without necessity to go through them, and we take into account only distance to them, then we get the regression line in the form plus 0.5, well, the red line. And they have different angular, different signs of angular coefficients. So the situation is very, very interesting. But anyway, it is really the best fit line. The red line and the green line. And to finish my presentation, I present you the third line, dashed line. The dashed line is a result of applying symbolic data regression according to the very first method, midpoint, that takes into account only midpoints of the intervals proposed by Billard and Bidet in 2000. It has angular coefficient 0. It's a compromise between these two lines. That's all. I appreciate your attention.
Okay, many thanks, Sergey, for your very detailed and interesting presentation. And yes, as you just mentioned, the floor is now open for discussion. Is there anyone who wants to ask a question to Sergey?
Well, there are no questions. I say to students.
We have a question from Marek.
Either everything is clear or nothing clear.
Well, more or less clear, but my problem is that you are using some distance between interval and points also.
Yes,
but,
in the last approach, non-enclosing data, non-enclosing, yes.
We have many distances. Which one do you use and why? Yes,
you are right. I can use many distances. At this point, well, I asserted that deviation of the regression line from interval data may be just any norm of the vector made up of a separate deviation for uncertainty boxes. But what do you mean? This point for my choice of the distance for a separate uncertainty box. Because this construction is also, well, questionable. You can ask about some details.
My question has the reason that if you use different distance function, then you will obtain different results.
Yes, of course. We used Chebyshev norm because we have because Chebyshev norm is usually non-smooth, and it has a clear probabilistic interpretation. It corresponds to the maximum likelihood method for uniform probabilistic distributions. Do you know? Yes? Well, and preserving the smoothness was not important for us because we have good non-smooth optimization techniques developed by my colleagues from Ukraine, from Vladivostok. So we just adapted it to the situation, and it is a optimization, the same optimization method as I used in my maximum compatibility method for maximizing the recognizing functional. So yes, you are right, different results. Yes, I do not discuss that because it is very preliminary, but I just wanted to show you that the main tendency that enclosing and non-enclosing data, they produce even opposite tendencies for the data. I think that for non-enclosing data, if you used another norm not Chebyshev, for example, Euclidean norm or one norm, the sum of absolute values, you will get something similar to the red line with positive angular coefficient, but I used it just to illustrate the general tendency. I do not insist on the result. I will research it further.
All right, thank you.
We have the next question in the audience, this time from Luc.
Yeah, thank you, Sergey. Very nice presentation. I discovered symbolic data analysis because I didn't know that before, and I would like to know if there is some links between symbolic data analysis and with a Bayesian method, or is totally different.
Tell me the question once again, because
okay. So you can hear me, yes?
Yes, yes. I
okay.
adjusted the volume of my speakers.
Okay. So yes, so I discovered symbolic data analysis, and it seems very interesting. And I would like to know if there is some links between symbolic data analysis and classical Bayesian theory, or if it is totally different.
I do not know the precise answer to the question, because I myself, yes, I understand the symbolic data analysis well to some extent, but I do not know. You see that my applications to Billard and Day, they are unanswered on ResearchGate. Recently, Brazilian people responded, and they invited me to their conference, and maybe I will be able to answer some questions, and yours one, this conference, but they behave themselves as if they are the mainstream in statistics of interval data, and we are as something secondary, well, in statistics. I showed you the examples.
Okay.
I think that situation will change in the long run, yes, but right now I do not know. Maybe. I can provide you with some papers if you wish.
I think they are quite easy to. I just try on internet, and it's quite easy to find them. I will have a look. I will tell you. Okay, thank you very much.
Okay, do we have any further questions? Okay, I do not see any further question at the moment here, either in the chat or no one else has raised their hand. But maybe let me ask one question. What you did so far is this was more or less an, let's say, some kind of identification task when already all the data are available. Did you consider also in some of your works, let's say, some questions concerning an optimal design of experiment, in which, for example, you already know that a linear fit would be appropriate for modeling some system, either static or dynamic system, and that you want to gather the data by a suitable experiment that, for example, minimizes some kind of distances that you have introduced, or that maximizes the likelihood to find some covering relations at the end?
A very interesting question that outlines further lines of research. Yes, I bear that in my mind, optimal design of experiments, but I do not know yet. Maybe I have some thoughts, but I do not want to pronounce them, not to be maybe too premature, too funny, because yes, I prefer to pronounce some solid conclusions. Yes, obvious. Yes, it is the next step in my research. You see that in theory, in developing theory, every step should be made clearly and in convincing way, because people who criticize us, who consume our results, they should be totally satisfied within some small space of the theory. So I do not know. I do not know right now. Well, it is a very interesting question, yes. But
I think it may have some relations also to the question that Marek has asked, because the definition of a distance is not clear. And I think definitely also the definition of a distance will change, for example, also the outcome of your optimal experiment design then at the end.
Yes, yes. I should say that for some interval analysis methods, for example, for maximum compatibility method, we got the probabilistic interpretation jointly with Vladimir Klinovich. We published a paper in 2016, and you maybe you have heard that our presentation, joint presentation, it's Scan 2020, devoted to the probabilistic sense of the tolerable solution set. Yes, and so we move in this direction, but slowly, very slowly, but very seriously.
Well, that's definitely, on the one hand, a very challenging question and also very interesting questions.
Yes.
Okay, we have the next one who has raised their hand.
Yes,
Alan Kumar.
Should I have should I send you my presentation PDF, for example?
Yes, please send me the PDF at the end. I'll put it on the webpage. But now we have a question from Alan Kumar.
Mm-hmm.
We cannot hear you at the moment.
We can read, maybe.
Yes, maybe if your microphone doesn't work, you can type in the question in the chat.
Mm-hmm.
Hello.
Okay, now it's working.
Okay, perfect. Hi. Yeah, I mean, one of the main advantages of using interval analysis is that you can propagate the measurement uncertainty to the parameters that you want to estimate. And I'm wondering now for the other method, if it is possible. I mean, you don't have uncertainty measurement for the parameters that you estimate, right?
I did not tell about this uncertainty, but actually, yes, it exists. If I told you about these problems, that would take not 1 hour, but maybe several hours.
Okay.
Yes, you have such information set, and the next step is how to get estimates of this information set, out estimates, in estimates. Yes, I can do that. I just
I think this is
did not tell about that in my today presentation because of a lack of time.
Yeah, okay, I understand. But I think this is also something quite interesting. I mean, or if it's, for example, localization or something, then you're always interested in the parameters that you estimate. And then you can compare perhaps, at least empirically, if the true solution is within that estimated set, for example, to compare the methods, at least empirically.
Well, I have to remind you some basic concepts of interval data analysis. Information set that you can see at this slide, it is a set of parameters compatible with the data. Mm-hmm. And so it makes sense only for enclosing data. For non-enclosing data, it doesn't make sense. You have only point estimate. Well, that best fits. But for information set is the set of points that are compatible, and it is a solution. Usually, it is a solution set to interval system equations constructed from the data and from the expression for the function. So I can do everything with this information set because it is solution set in some sense. Well, and so what do you need? You can use any techniques of the interval analysis for enclosing it, for computing inner boxes, and so forth. You see that interval data analysis, interval statistics of interval data, it is It has conceptually, it is different from classical statistics. Yes, we have some very similar concepts. And for example, I tried to introduce a concept of variability at scan to 2020, and then analog to standard quadratic deviation and such like characteristics from the standard statistics, traditional probabilistic statistics. But so far it is not developed. I think it is the matter of future development, and you will see everything in the near future.
Okay. Yeah, okay. Yeah, thank you very much.
Okay, do we have further questions? I think this doesn't seem to be the case. Then again, many thanks, Sergey, for your interesting presentations. Also for lots of details that you have given and for your patience in answering all the questions. And yes, from my point of view, it's just time to now wish you a nice Friday afternoon, evening, and weekend. And
Yes.
we'll see each other again very soon in 2 weeks.
Mhm.